Hello everyone, so just a quick announcement that I'm starting a new series of videos which is going to be me trying to derive various things or explain various things on a whiteboard. Now I will keep the not so fast videos which are meant to combine equations, sometimes simulations and some sort of animations about some common misunderstanding or things that are not explained necessarily in details or in fact never explained in most texts. Um, but that being said, there are plenty of other things that are not discussed, or at least that are kind of seen very fast, and that are much more technical, and that deserve to be dealt, let's say, a bit more thoroughly on the board, um, so that basically you can see exactly how the calculations are done, and that this particular kind of discussion does not really lend itself to a presentation on PowerPoint. I think it's much better to see that directly on the board, and you can follow along what I'm doing. And in fact, if you don't understand what I'm doing, then you can ask questions, and then I can actually cover that in a different video. Okay, so today is the first, in fact, of the series, and that's going to be about the curl and whether we can provide a mechanical interpretation or analogy at least for the curl. Hello everyone. So in this video, what we are going to discuss is the curl, and we are going to try to interpret and provide an interpretation of the curl that is going to enable us to better appreciate what it is and serve as a sort of diagnostic test to see whether a particular field has maybe a non-zero curl or not. So often the curl, when you learn kind of basic vector calculus, the curl is the one with the most difficulties, or at least that poses the most difficulties. And most of the time, students and in fact teachers alike tend to remember an intuition about the curl that may be misleading. And I think this is quite well captured by these two possible fields. So here, by the way, these fields are borrowed um, from fluid dynamics. So the one here, so let's actually do this way. So this particular field, you see, it corresponds to so-called laminar flow, but it's not really important here. But corresponds to essentially field lines that are perfectly horizontal. Okay. In fact, sorry, I need to draw back these arrows here. So essentially the field lines are perfectly horizontal, and you've got that the magnitude of the field is going simply to depend on kind of the value on the y-axis, and that's it. It's dependent on x. However, it's directed in the x direction. Okay, so this is called a shear flow if you're looking at hydrodynamics, for example. Now, on the other hand, we've got here this particular field, which is a sort of rotating field, and that corresponds to a vortex field in fluid dynamics, but that could be any force field you have in mind. In fact, it does correspond to also a force field in electromagnetism as well. But the bottom line is that you've got this thing circling around some origin point, and that's it. Now, the expressions of these two fields, aside from being drawn here, is for the left-hand side one, this is simply proportional to y, and then in the x direction. While here it's a bit more complicated. It's actually cx over square root of x squared plus y squared in the y direction, then minus cy over square root of x squared plus y squared in the x direction. Okay. Now, a much easier way to actually write this guy is simply c over r and then in the theta direction. Now, this is when you work in polar coordinate system, including the basis, And that's what I've represented here. So you've got the distance here from the origin to the point of interest. That has so that's the distance r here. Then you've got the radial vector there that is radially emitted, let's say, from the origin, you could say. And then theta here is the vector perpendicular to the radial direction. That essentially goes along the rotation direction. Now, when students are confronted for the first time to these particular fields, the intuition goes as follows. Here, there is basically a flat, like a set of flat lines that are not kind of turning or anything like this. And so the sentiment is that this field should have curl 0. While here, there is basically, the field is curling over, if you will, by doing these rotations. And therefore, the expectation is that this should have a non-zero curl. Okay, so that's the bottom line. And what we are going to see is to try to explain that this intuition can be misleading. Okay, now, of course, if you do not have this particular intuition, then that's great for you. But hopefully you will still learn that there is some interesting mechanical analogy that can be made. Now, the way we are going to make this analogy to understand the curl, so the curl, by the way, here I denote it as the nabla symbol, and then cross product with f, the field, and then here, this is the Stokes theorem. So the Stokes theorem is going to tell you that if you take the flux of the curl of the field and then across an area bounded by a curve, then this is equal to the line integral, in fact the so-called circulation integral of the field along this curve gamma. Okay, so the way we are going to evaluate, estimate, and interpret curl here is basically by trying to understand what the circulation actually means, what the circulation of this thing on any curve actually means. And what we are going to do is basically try to use the fact that because this has to be true for any curve gamma, then it has to be true for also the simplest curve we can think of, which is a disk or a circle. Okay, and that's what we are going to do here. So let's imagine we've got a circle here, and then the origin is O, and we've got a radius r for that circle. Imagine, by the way, that I actually painted the actual line here, and with a marker I put the radius r as well, so that if there is anything going on with regards to this thing rotating, for example, then I can actually visually see it if you imagine this has been painted on the disk or the circle you're looking at. So basically now gamma is going to be the circumference of the circle I'm looking at. Okay, and what I want to do is that I want to consider a field F, okay, which is going to act on the surface, on surface points of the sphere, of the disk. Okay, and so it's going to act as a force. And so, for example, what that means is that if the force field here is in green, then at any point you can have the F doing something. Okay, so here, there, and so on. Okay, so that's the force field F, and you can take whatever direction you want. That's kind of it. And so what we want to evaluate here is the total moment on that particular, acting on that sphere. Now, the moment in mechanics is a quantity that is going to tell you whether the object you're looking at is going to have a torque applied to it. Essentially, that's it. And so that's why the moment has a sort of lever component that is basically the distance to the axis of rotation, and then there is a force component to it. So here, for example, the lever is from the origin. If you're interested in rotation about the origin, the lever length is always r. And that's something we are going to use here. So the total moment here, we need to sum over all forces acting on the circumference here. And we need to say that this is with respect to the origin. And that's going to be equal to the integral over gamma. Gamma here again is the circumference of the circle. And that's R cross F. So that's the definition. And that's it. So that's this, and then dl. And dl here is the quantity. It's simply the elementary arc length there. Okay, so that's the first thing we can say. So that's the formula that gives you the total moment, like the resultant or resulting moment from all the forces acting on the sphere. Now, what we want to do is realize that when you calculate the r cross f, both of these r by the way, is actually the position vector indicating the position of a point on the circle, okay, from the origin. And so what we have here is that in the end, we've got a vector r and we've got a vector f. Both of them are in the plane of the board here. So what that means is that when you take the cross products, they are going to return a vector which is perpendicular to the board, okay? And this vector is going to be along the z direction. So I'm going to call that z, and z is pointing that way, okay? So what I can calculate, because there is no other direction for the moment when I'm writing these things on the board in 2D, then what that means is that I can calculate the z component, which is the full magnitude, in fact, of the moment, as being the integral from gamma, and then I've got r cross f, and then I've got dot z, and then dl. And there is something interesting that actually comes, that when you try to find out what is the magnitude of r cross f, you're going to see that r takes always the same magnitude, right? It's simply the radius of the circle, so nothing crazy about this. But then the non-zero contribution to the cross product has to stem from only one component of f. So if you actually split, for example, let's look at this guy here, and there is a radial component, yeah, which is not well actually drawn. So there is like this. So that's the radial component, and then we've got a perpendicular kind of theta component here. So what we have is that the force can be divided into a tangential component and a radial component. Okay, so that's starting from the origin. Okay, not well done. But essentially, you need to understand that the force can be split into a radial and a theta component. And the only component that is going to work, and in the sense of providing a non-zero contribution to the cross product, is actually this one. Okay, that turned out to be perpendicular to R, but also tangential to the actual circle. Okay, so the result we get at the end is this one. We get that this is the integral, again, of a gamma, which is a circle, of the radius r, which is always the same, okay? And then here I've got f, and I know that the component that matters turns out to be the component which is tangential to the circle. So in fact, here I'm going to write f, and then tangential to circle, and then dl. But it turns out that f tangential or parallel to the circle dl is also, I can also write it as being f, the scalar product of f with dl. Okay? And so if I actually write this like this, I can remove the r from the integral because r is unchanging. And then I've got the r, and then integral of f dot dl, where dl here is a vector that has magnitude, arc length, elementary arc length, and then the direction here along the circle. Okay? So in the end, I actually can get the following interpretation of the circulation of f, is that the circulation of f along a circular contour is actually equal to the moment divided by r. Okay, so you see that what happens is that if you want to interpret what the circulation of a force or a field means along a particular circular curve, then in that case you can say that this is equal to the moment exerted by that particular field and then divided by r. So it means that it makes the magnitude of that moment independent of the level length. Okay, and that's what you want because you want something that is not going to depend on how big your radius is going to be. Okay, so that's the bottom line, and essentially in practice, what this tells you is that essentially if you have a non-zero curl, and that's only possible if also you need to be careful if you want to use that theorem, you need to make sure that both f and the curl of f are defined within the area that is bounded by gamma over which you want to integrate. But if this condition is met, then if this curl is non-zero, the flux is going to be and the flux is non-zero. So they need to be kind of collinear or something like this. Then it means that essentially the circulation is non-zero. And if the circulation is non-zero, then it tells you that there is an actual positive total moment and is therefore a torque applied to the circle, and you would expect therefore that the circle rotates. Okay, so that's kind of the bottom line. So in application, what that means is that let's take, for example, this one here. Now let's imagine that these are actually two different time situations, and I actually draw here a ball, if you will, and then I put an actual painted mark on it so that I can tell whether it's rotated or not. Now, as you can see, the magnitude of the field at the top is going to be larger than the magnitude of the field at the bottom. And because we are here in the x and y direction, then essentially we are going to get that the length, dx, or that is traveled at the bottom and top when you do the circulation, when you do the f dot dl, L dot dl, you're simply going to get f dx. And the dx here is going to be the same whether you are at the bottom or the top. So nothing is going to change there. And so the actual difference here is going to be meaningful and going to provide a torque, if you interpret that as a force field, onto a circular kind of ball. So over time, the ball is going to move from the left to the right. So there is a translation force. But then on top of that, it turns out that there is a rotation as well of the circle here from horizontal, let's say, to more vertical down. Okay, so that's clockwise rotation here. Now you can try to play the same game, for example, here. So you imagine a ball that is initially here, and then it is there. So this is at different times. So here this is t equals 0, and let's say there is a mark here, and then t larger than 0, and let's say we can try to see what the mark is going to be there. So at t equals 0, what we see is that there is a larger value on that side than on that side. So our initial impression from what we've seen so far is that there should be a rotation in that direction. So again, clockwise rotation here. while the flow is actually anti-clockwise. Okay, but here there is a slight subtlety, and the subtlety is the following. When you calculate the element of integration for the circulation, what you notice is that this is going to be c over r theta in polar coordinates, and then the dot product with dl. And dl in polar coordinates is r d theta and then theta here as well. So what you get in the end is that you got c and then d theta. So what you find is that if you take a circulation that is along, for example, something like this, then you're going to get the circles. So let's do it this way. Okay, so the circles here are smaller than they are here. Okay, and they are smaller by the same amount than the vector here is bigger than this one. Okay, by the same magnitude, if you will. And therefore, what happens in the end is that the actual product of the two is going to be constant. And so this let's say, part here contributes the same as this part to the circulation. And therefore, there is actually no curl. So there is no net torque acting on the particle. And you can say that there is no curl wherever you are not at the origin. Because at the origin, we said that earlier, the field is not defined. So the bottom line here is that there wouldn't be any rotation. So here you would have that the curl of F is actually equal to 0 for any R that is different from 0. While here, actually you would get that the curl of F is different, is equal to 0, and here is different from 0, and that's for any point. If you want to play with it in R2. Okay? So basically that's kind of the idea. Um, there is a mechanical interpretation that can be made about the curl, and it has to do with it, virtually, if you will, inserting a disk, a sphere, or a circle in a field and try to determine whether or not there's going to be a torque acting on it if we interpret that field as being a force field acting on the surface points of the object, of the circular object you have actually put there. So of course, this thing can be also put in 3D. What happens in 3D is that you've got different directions that are possible, and in which case the directions are going to tell you that you may get 0 in some directions, but not 0 in some others. Okay, so instead of one value, you get 3 values, obviously for the torque, for the curl, and these 3 values are going to tell you whether there's a tendency to have a rotation of the object about, let's say, its center of mass, um, uh, based or related to the field. Okay, so I hope that it's made at least clearer what the curl is about and how you can pinpoint quite quickly whether something may have a curl, a non-zero curl or not. And then basically, I hope that you will find some other examples. So if you find some other examples that you would like I treat in this kind of board discussion, then please do let me know. And otherwise, we see each other in the next video.